All right, thanks. Thanks for having me. Thanks for inviting me over Tony. My name is Tuomas Artman. I've been working for the past 4 years at Uber in San Francisco. Essentially, I'm on the mobile platform team. What that means is we create or we define how Uber builds their mobile application. We spend a lot of time, doing R&D on architecture, building out frameworks, and essentially building out the tooling that all the mobile engineers that build products at Uber use. The most recent things that you might have noticed where we've had our hand in is the rider redesign. If you ever used Uber, you might have noticed that a year ago we launched a fully new rider application, and that was sort of I was part of the team defining the architecture, figuring out how 400 mobile engineers can work together in one code base, which is an interesting challenge to have, and obviously a great experience for myself. Although I don't think that I'll ever need that knowledge again if I go to other companies, because it's not very usual that you have that big of an engineering force working on a few applications. Today I'm going to talk about cross-platform development at Uber, and specifically I've got 3 things I want to talk about. I want to talk about why we built almost everything natively as opposed to cross-platform. Bit of a different vibe than the forum that we're convened here for. But I want to give you sort of an example of why we made that decision and what actually the business reasons behind this is. Because oftentimes mobile engineers and engineers in general, they don't make the decisions based on business impact itself, but they make decisions on ease of use or ease of engineering, ease of development. Cross-platform sounds very nice because you don't have to go twice for both platforms. But I'm going to give a few of the reasons why we've decided to build most of the stuff natively. Then I'm going to talk about what we do when we don't build things natively. We do have a few applications that build with React Native. We're working on our own technology to do cross-platform development, which has been my main project for the past year. And lastly, I'm going to talk about sharing native designs across platforms. So what happens when you have big applications and you want to share as much as possible between the different platforms? What did we come up with? What did we do for that? So starting off with why we built almost everything natively. The first thing is that performance really matters. It might not be obvious, or maybe it's trivial for everybody that sure, a performing app is much better than a non-performing application. But what is really the business impact of performance? Secondly, I'm going to talk about reliability. Why reliability, especially in mobile applications, is super critical. So starting off with, I'm going to reset the slide because the animations don't work nicely, and I'm a guy for animations. So let's see, maybe we get some nice animations now. Why does performance matter? Here's the rider application across the world, and an indication of the device, the device age per se, for iOS devices that run the application. The device class that we use is, on iOS it's simple. It's essentially the year that the device came out. On Android, it's less clear because not every producer, not every manufacturer produces a better device every single year. So we use a classification inspired by Facebook, where you use something like CPU and memory to classify a device to be of a certain age. This gives you a rough approximation of the performance capabilities of a device. On iOS, it looks pretty decent. We've got bigger than 2017 device classes, which essentially is an iPhone 8 and iPhone 10, being at 15%. And even the lowest one, I think that's an iPhone 5, is at 7%. And literally no iPhone 4Ss or iPhone 4s anymore, so we really don't test on those devices anymore. So on the low end, you have pretty good devices as well. All of them are multi-core. All of them have enough memory to run an application. All of them have pretty good GPUs. Now, if you look at Android, it is not that good anymore. You can see that a lot fewer devices are super high-end, and you've got a much longer tail in the back. So you've got 1% of 2010 devices which is when Nokia still had like 30% market share, which is pretty annoying. So because we cater for everybody in the world, and we want to create a transportation system that runs as reliable as water throughout the world for everybody, we need to take these things into account. I'm sure these numbers will be, roughly very different in Finland and in Europe, but we have to really think about what can we do in order to cater to those users with those low-end devices as well. So from a my next slide went. Hold on one sec. I need to know what my next slide is. There we go. So my thesis is, or our thesis was, that application performance will have an effect on your bottom line. And about a year ago, we started looking into performance on the platform team, and we essentially expanded that to every single team and created a task force to look into what the business impact of performance is, and then fixing performance issues and making it as fast as possible. And here's two examples that we did. First, on the left side, if you look at an iOS improvement in performance, we've got tap performance being on the unoptimized side pretty bad. So when you tap, it takes a while until your product selection comes out. And that was due to a number of things. We were doing all kinds of things in the background, like sending analytics that could be deferred, and simply, our bringing up the screen wasn't optimized. So we went in, instrumented the application, and figured out how to make it much faster, essentially instantaneous. On the right-hand side, which we actually measured nicely, was an optimization that we did for Android. And we essentially, looked at the map loading up, and it was super slow before our optimizations. And it wasn't really clear why that was. And we had to go pretty deep into the operating system itself to figure out why that was. Because again, you don't own that code. Google Maps provides you an SDK. You tell it to load up. You can look at what else your code is doing. But apart from that, it's pretty much a black box without going too deep into performance analytics. We were able to figure out what was wrong, do some optimizations. And the experience you see on the right is the experience that we currently have. So the map on low-end devices just loads much faster, and is much more optimized. And this would seem like a trivial thing. Like, sure, it's nice to have, but is it really critical? Is it really crucial? So we obviously A/B tested this because we A/B test every single thing that we put out. And the results were pretty staggering. I can't tell you the direct numbers, but I did some calculations, and we could have put 400 engineers just working on that one screen, for the rest of our lifetime, and it would have still made a difference. It would have still been a positive business impact. So even though a performance improvement might look like a nice-to-have thing, there are real consequences on your bottom line. If your application doesn't perform well, your users can switch to a different vendor. They can not use you because it feels sluggish. And if you make any improvement in your application, you will see an increase in retention. You will see more consumers stick with your platform, and that can have a really potential impact on your business itself. And that is not something that was obvious to us in the beginning. Everybody knew that we wanted a high-performing application, but it wasn't clear what the business impact of that is. Which brings me to the realization that performance optimization is really hard. For example, for this case that I just showed you, we had to build our own tooling. On Android, it wasn't clear why the performance was so bad. So what we did is we forked the Android operating system, because that's what you do when you want to go deep. And we put in hooks into function calls themselves, so that we could trace out native function calls and virtual function calls. And what it would do is you would run your application, you would launch Nanoscope on your CLI, and it will gather every single function call that happens in the system, be it virtual or be it in the operating system itself. And that essentially revealed to us a bunch of things that happen when views get constructed, what happens inside Google Maps when it does its thing, and led us to be able to improve the performance of the application like this. And this was a pretty long project to actually get to this state. We started with normal debugging tooling that comes with Android Studio, and that essentially let us somewhere, but not all the way down. And we came up with Nanoscope, which is essentially 1,000 times faster than what comes with Android Studio. And it lets you, without essentially any performance hits on your running application, measure what is going on in your application. It's open source. If you want to take a look at it, it's up on our GitHub. So native performance optimization is very hard. But if you add a cross-platform framework on top of that, it becomes you're just adding things on top of your application that you don't control, but you can't do anything about. If you have performance problem in an application, sure, you can optimize your business logic, your code, but when it goes into the framework, there's really nothing you can do about it. If you use React Native, they've spent 2 years trying to optimize the framework and make it as fast as possible, but still they weren't able to push it all the way to make it as performant as native development. And you, as a probably pretty small team, you don't want to be wasting your time optimizing a framework that you're just using. So it becomes critically important to figure out what the performance business impact of your application is and what you can do about it. So the first thing that I want you to take away from this is you need to measure your application. You need to know what the business metrics are that are affected. You need to know how startup time, type responsiveness, yank, if you have frame drops in your application, performs and how it impacts your business. You don't really want to optimize beforehand and then do the A/B test, because that is hard and you spend a lot of time, and it might actually not make any difference because maybe you don't have any competitors. Maybe your application is the only one that can be used. But what you can do is you can run a negative A/B test. Essentially, you can make it worse for some people. You can increase the startup time by, say, 3 seconds or 5 seconds. You can make a critical tab less responsive. You can add some jitter in there where every 10th frame is dropped, and the UI becomes less responsive. And you can A/B test what the impact of that is. Super simple to do, will not take you a long time, and through that A/B test you can get to the actual cost of your performance. You can say how many euros it costs for your startup to be a second slower, and I guarantee you that there will be an impact. I just don't know what the impact is for your application. So you should definitely try it out. And once you know what the cost of the performance is, then compare it against the cost of building natively. If you build native applications, you're probably spending more money on R&D. It takes you a bit longer to develop that, but at least you have now a framework that lets you make the right decision. You can say, if you build it as a cross-platform product, we will have this hit on retention, but that monetary wise means this amount of money. If that amount of money is less than the cost of building 2 applications, then you probably should do it. Lastly, it's good to keep in mind that cross-platform development is not twice as fast as native development. People usually say that you have to develop your application twice, and yes, that's true. You have 2 platforms to support, but it's definitely not twice the cost. If you think about feature development, design, all of those can be shared. You can have maybe an architecture that is shared. You can build frameworks that both of your applications can use, making development easier. And you have to figure out how to create a UI for Android and iOS, unless you really want to go the low route of just making it look similar, and all your Android users will be unhappy, or your iOS users, depending on what design you choose. So it's not twice the cost, and debugging and testing is a cost as well that you have to do still for both platforms if you use a cross-platform technology. So don't just make it twice as big and say that this is the cost of going native. The second one is reliability for mobile applications. And what you see here is essentially all the versions of our clients out on Android. I think I took this screenshot like 2 weeks ago. You see our versions. Our versioning scheme is pretty simple. We've got the minor version, and every single increase in that version is 1 week. Because we ship our application every week, we increase the minor version every single week. So essentially every bar here is a week older client. And this doesn't look too bad. Like, sure, you don't have an adaption. It's actually much nicer. For some reason, iOS engineers or iOS people just auto upgrade their applications, and your application gets upgraded. You still have a long tail, and you have a pretty darn big long tail. If you stack all of these older versions up, and it doesn't stop here, but you have a tail of essentially going 2 years back. You have a lot of percent of your users being on very old application versions. And what that means in mobile development is your application needs to be super reliable. Once you ship it, once you push it up to the App Store, it's out there and you can't change it. It's been done, so to say. If you have a critical bug that kills that version or makes it impossible to use, you cannot take it back anymore. All those users that installed the application, which will be a pretty big user base, have that application version, and they might decide never to move forward again. So it's not like web development where a bug can be replaced on the server side by just pushing the new version of the client. Mobile versions are out there, and you might think, well, if that's the case, if you encounter a huge problem, why don't you just force upgrade everybody? Let's put in a mechanism saying, if you're below this version, we just show you a dialog saying, please download the latest version. Well, we did that for a while until somebody smart enough said, well, we should probably measure this, how much it costs us to automatically upgrade 3-month-old clients. And it was staggering again, how much money we lost by force upgrading people. Because when you are on the road and you want to take an Uber, and the application tells you that you have to upgrade, it is a pretty big download in order to get that Uber. So many people didn't. They switched to alternatives, they maybe walked, but we lost a lot of users by force upgrading people. So essentially just said, we'll never force upgrade again, unless something really critical happens and we just have to. We just have people enjoy their version that they have. And if they want to be on a 2-year-old version, let's have them there. If you want to upgrade people, let's present them with a dialog saying, hey, you're on a very old version, you should check out the latest features. But never force them to do so. So if you can't get rid of old clients, and you get into problems where a single misstep in your code base or in your release might actually kill that specific version and make it unusable, or have a nasty bug that clients will hate you for, or have a performance regression, why can't we just dynamically download everything? Because again, cross-platform, some of the technologies are JavaScript based, so you could have your entire application just written in JavaScript or some other tooling, and you could download it over the internet. And that might be a good idea, unless had in common for us that the devices are pretty slow and the network is pretty crappy. This is a figure from, I think it's New Delhi. Only people who are not on Wi-Fi connections, so people who are roaming out in the wild and take an Uber just using their cellular connection. And it could be worse. Like, I would have imagined actually these figures to be worse when I dug in. 75% of all requests that we make from the clients come back in about a second, which is pretty decent for bad connections. But it's the problem that comes again in the long tail. If you look at 95% of requests come back in 4.8 seconds, that is a pretty noticeable lag on the user side for every single request. And you might have to make a few requests to get an Uber or display some content. And even worse, if you really care about your users and about the long tail and the 1%, those requests take more than 35 seconds. And that essentially means it's unusable. You cannot use the product if you're in New Delhi, unless you have the patience of an angel. It is now impossible to wait for that. You would imagine that something has gone wrong. So for us, it's really not possible to download the entire application over the wire because most of our users are on cellular connections, and those connections can be very slow. Furthermore, this increasingly becomes harder the more you download in one request. It is not exponential, but it's close to exponential due to packet loss and changing of Wi-Fi towers. Sometimes the client just starts reloading everything from the scratch, drops all the packets on the floor that it has received, and goes back and refetches all the content. And that can mean that if you go above 100K, 200K, it will simply never load. For 1% of users who are in a bad spot, it will never complete. And if you think about React Native, for example, which is the most popular cross-platform technology, the basic example of a React application, if you just do a hello world, gzip it, it's 160 kilobytes. And that for us is just way too much. Like, we want to keep our packets, hopefully under 1 MTU, which is a mobile transit unit, and that's 1.5 kilobytes. Going above that, we need to have a reason why the payload is so large. There's some things where you send up a lot of analytics, for example, where we go over that. But we try to keep it very, very small in order to cater to the long tail of users. So what we said is, we want 99.99% reliability, 4 nines of reliability on our mobile applications. And we've spent a ton of time, doing this and trying to make sure that we can create applications that always work, that, we catch all the regressions, even at compile time. If not at compile time, we have nice testing suites that catch any problems that we do. And this is actually, I just took a screenshot from Crashlytics. It says 100% crash-free users for all builds. To having no crashes at all. Most of the crashes that happen in our clients come from Apple's networking stack or Google Maps or third-party vendors that we have no control over. The same would happen most likely if you were using a framework to do so. Whenever you add a new dependency that you don't have control over, you open yourself up to having crashes in your applications. And I don't know how much that costs you, but you probably should figure out. So what can you do in order to make mobile applications very performant? You can have statically typed languages. That literally is the best thing that you can do. You can try to catch all the problems at compile time rather than at runtime. If you're using something like JavaScript, essentially you have to unit test every single character in your code, because otherwise you might have runtime problems. So we use Swift and Java to catch many problems at compile time, obviously, because we're building natively. We have optionality as a type, either through the language in Swift. We've got awesome optional types. If we can't do that, we use static analysis to make sure that every single type that can be optional is tagged. So we add that on top of the language in Java. So we will have no null pointer exceptions. At least that's a theory. There's obviously some gaps in the static analysis, but on Swift that is pretty much true. Like, we have not crashed on a null pointer exception in our code. We can use static analysis to find all kinds of problems that we have in our code base. We can enforce certain patterns that we found or deemed to be dangerous. We always look at our outages that we have in order to figure out what can we do better in order to not have this problem again. And we've got a dedicated team essentially going through these problems and looking at making the ecosystem of development better so that we don't run into these problems again. No runtime errors is super important. Whenever you can make the decision of crashing at compile time or at static linting, we will do that. Runtime errors are horrible because you essentially open yourself up to crashes when the user runs your code. And sure, you have logging in place to catch those, but the earlier you can tell the engineer that something is wrong, the better. And we have shared specifications with the backend, meaning that anything that the backend sends us has a spec. We use Thrift, and we code gen all of our interfaces for the mobile clients from that. So we can be assured that whenever the server responds to a request, we know what is being sent over, it has been validated on the server side before it's sent to the mobile client, and the mobile client will do its own validation and drop the packet if something's amiss, if a required property isn't there, for example. So no more problems with networking, or at least we get alerted very early on the backend side. And lastly, we have a good testing permit in place to catch all kinds of business logic mistakes through unit tests and integration tests. And lastly, we do smoke testing. So we have our engineers who checks their feature whenever we have a build, and that takes quite a long time, unfortunately, but we're working on making that automated. So if you go to any other development environment and you choose JavaScript essentially as your technology choice to build out your cross-platform application, none of those things apply. Like you can still have shared specifications with the backend, and you can have a testing permit, but all these other fail-safes that probably account for 98% of all the things that we catch at compile time are gone. You can change that with one simple thing: just move on to a type language and use a transpiler to transpile from either TypeScript or Flow to JavaScript. I can't say how important this is to do. Like I would not recommend writing anything in JavaScript in this age. And these tools are awesome, and they catch so many problems that you write, and will essentially help you reduce your crash free rate or any problem rate by at least 90% by catching all of these things at compile time. So again, the takeaway here is, simply use a strongly typed transpiled language if you choose a cross-platform technology that is based on JavaScript. And secondly, again, understand the cost of your outages. Like you need to have some sort of metric that you compare yourself against in the reliability aspect as well. You need to figure out how much it costs if you crash or have an outage for a week, because it takes a week for you to ship a new version of the client, how many clients you lose because you have these outages. And really the best way to do this is, again, well, you can't really A/B test this. Obviously, you could add crashes in there and figure out what the cost of that is, pretty radical. But you could look at the adoption of every single version until you at some point have an outage, until there's a problem with your application. And then you compare that application versions to the previous application versions that didn't have any problems. Sure, the application might have changed in radical ways, and that makes that comparison invalid. But at least you have some basis to figure it out. And then from that, you can go on and figure out whether you want to do native development or whether you want to use cross-platform technologies. So what do we do when we don't build natively? At Uber, we have a few applications that we do in React Native. The biggest one is, if you've heard of Uber Eats, it's essentially Wolt, but like 500 times bigger in the world. Sorry, I had to do that. It's essentially a food delivery service where an Uber Eats user can request something from a restaurant which has an iPad. That request goes in, the restaurant prepares that food, and then a Uber driver is dispatched to pick up that food and deliver it to the user. And we decided to go with React Native for the restaurant application. Essentially, we went in and said, we want to do this trial because it's a pretty controlled environment. We know that iPads, they always have Wi-Fi connectivity. Every single restaurant has Wi-Fi. We know all the users, so we can reach out to them in case there's a problem. We can force upgrade them if need be. They're much more receptive to us, making changes to the application and them uploading, simply because the business is tied to that application. And in other parts, like we have looked into figuring out whether we could build something cross-platform, because we've got tons of forums and simple screens that have an image and a bit of text. Or we have, for example, have driver onboarding. So when you want to become an Uber driver, there's this questionnaire that you have to do, and this questionnaire is different in every single city in your world, and it has 120 different screens that are all just essentially text input, or taking a few pictures, or selecting a GPS location. And it sort of doesn't feel right to have to build these twice, because it's mundane. It's pretty simple. There's no reason for it to be super performant or look awesome. because it's essentially a very simple screen. So we looked at all the cross-platform technologies that you can use React Native. Flutter is an interesting new thing that Google put out. You've got native, then you've got Xamarin, and then tons of other smaller ones that are probably not good for big application development, but might be useful for prototyping, etc. So we looked at all essentially these 5 technologies and figured what do we want from a cross-platform technology. The first one was that we want, because once we go cross-platform, we would really want to be able to download some feature updates from our backend services in case there's a huge problem, or even because regulations change in different cities and we need to inform the driver of different things. We would want to be able to not have to ship a new mobile client in order to release new features. So essentially that leaves us with 3 variants. Flutter and Xamarin produce native code, and you cannot download native code over the wire. Otherwise, Apple will just throw you out, and Google hopefully as well. So you have to go with JavaScript. JavaScript runtime JavaScript code is the only thing that you can download from the internet and then have your mobile application run. Well, once you go even further, like if you have this thing built in JavaScript, and we've got 2 platforms, iOS and Android, how about the web? Like, why can't we choose something that we can use on the web as well? Why can't we have 3 cross-platform development? So we wanted essentially a technology that you can develop once and then publish on the web, on Android and on iOS. So you've got essentially 2 options. You can make React Native work with the web as well. There are some frameworks that help you build one application that works on all 3 platforms. So that was essentially the choice that we were looking at: React Native and web views. So we looked at the first 2 things that I've talked about, which is performance and reliability. And then we started discussing more, and we came up with essentially these criteria that we wanted to measure these frameworks against: performance, reliability, versioning, reach, maintenance, dev experience. Performance reliability, we've talked about. Versioning is essentially the ability to make sure that when you deploy a new application, that your old clients will actually work with that application. React Native relies, for example, on you having built native components and then bridged to JavaScript code. So when you ship your new JavaScript code, you might accidentally use a component that is not in one of the clients that you're shipping to. So that's what I mean by versioning, guaranteeing that your application will work with all the clients that you have out there. Reach is what can you build with this? How many, how deep features can you do? What's the integration with runtime or with a mobile client? Maintenance, how much work is it for us to maintain the whole thing? And developer experience, how happy will our engineers be using this? And all of these are very important. And we looked at all of these things. And in the end, we realized that none of these things will work. If you look at just simply performance and reliability, well, not maybe reliability, but performance itself, React Native just wasn't up for par for us. It might be for you, but for us, it wasn't an option. It still requires you to spin up the JavaScript VM. Everything happens in JavaScript. It takes a long time. We produced a simple example of an application that has like 10 pages, measured it on the lowest end device that we still support, and it took 1.5 seconds to launch the application, which is React Native currently doesn't have the ability to sort of separate the core framework API from the application that you sell. I've got 15 minutes. Or at least 10 minutes. And yeah, so React Native, we weren't able to overcome the performance hits and figure out how we could optimize the packet that gets downloaded to be super small. Like everything comes in batches, and the minimum version. That's what you do, and nothing works. So we've been working on a technology called ScreenFlow, which essentially is a very similar tech than React Native. We internally call it native React, because we essentially is like building React applications, but everything runs natively. There's no JavaScript that renders a UI. You've got a declarative language that the mobile runtime can automatically consume and read out and render natively, and then the business logic is executed in the JavaScript VM. So we've got time to spin up the VM before the user actually presses or interacts with your application. I had a demo, but we're running late, so I can show this later. There's quite a bit more to talk about, and I can show this in between as well if you want to. So we essentially had to create our own technology that we hope our engineers will adapt going forward. Again, even though we as a platform team built these things, that doesn't mean that people at our company will actually use them, because we can't mandate any team to use anything particular. But we're betting on building out the technology and IDE, a compiler, to make it possible for people to build cross-platform applications. Lastly, my point about what do we do when we then build native? Like, most of our core features are still built using native code, and we want the performance that we can get. We want to be as close as to the metal as possible in order to make the user experience as good as possible. So we made the decision to build natively. But what can we do in order to make it easier to build applications for Android and iOS? So we created what we call RIBs, and what the community calls RIBs. It's an open source architecture for building mobile applications. It's, as far as I know, the first mobile application architecture that is both for iOS and Android. It uses the same terminology, it uses the same class names, it has the same concepts. Everything is the same across two different platforms. So what we did is 2 years ago, we were in a phase where our current architecture, at least on iOS, didn't scale anymore. We had grown from 5 engineers working on iOS to 150 engineers. And we started seeing problems that people weren't able to move fast. And they were toppling on top of each other because everything was intertwined, and the architecture just didn't compartmentalize things correctly. Just use MVC out of the box, and what you get is these massive view controllers. So we had the opportunity, because we were redesigning the entire application again, we had the opportunity to say, what would we do if we started from scratch? If we said, let's throw everything out and figure out how we should be building application. I won't bore you with these, tenants, but what we first did, we looked at 6 different tenants that we wanted the architecture to have. Reliable, we want to support Uber's growth for future years. We want to provide Rails for both code and design. Monitoring was super important for us. De-risking experimentation so that people move fast, and making magic. And we started this effort as with the iOS team. And when we get to this, we were like, hold on, this has absolutely nothing to do with our platform. This applies across the board. Like, why wouldn't Android want these things? Why wouldn't we work together as a bigger team to produce one architecture that works for both iOS and Android? Wouldn't that be fine? So we essentially decided to bring in Android as well and make this a group effort, and essentially say, let's build one thing out. And I don't think at that point we yet realized, how big of an impact that was. Essentially, what happened is we used to have these, or we still have these RFCs, requests for comments, which is what every team puts out when they build a new feature or new functionality. And when they do so, previously they would always have an RFC for iOS and an RFC for Android, because the implementation was so different. So they would put, as an iOS team, they would design how they would be building that feature. On Android, they would design how they would be building that feature. And the outcome was totally different implementations for essentially the same feature. And all of that stuff went away after we launched the new Rider application. We had the same architecture. Everybody nowadays just has one RFC, because there really is not that much difference between the two platforms. Sure, code-wise, you still have to produce the code twice. You still have to implement it twice, but you can use frameworks that we've built for them that are available. You can use, design specs. You can use everything that goes into the architecture across all platforms, and there is no need to design it twice. So that's at least one saving that we got out of it. So how we did it is, we spent a lot of time in January 16, starting with building out this core architecture and framework, and then eventually, gradually, we invited other people to come over. And over the course of 3 months, essentially everybody joined and ported their old features over to the new architecture and released the new application. And what we essentially built out in this 1 year, which was a huge effort, probably a team of 8 people working across iOS and Android, we built out the RIP architecture, which is essentially a core architecture to be building mobile applications at scale. And we built an application framework. All these bits and pieces that all of our mobile engineers needed in order to do their job. Things from networking to mapping, experimentation monitoring. Everybody needed that. So why not try to make the API essentially the same on both platforms, and try to at least align as much as possible on both of these platforms, and come up with one API for all of these different cases. And with that architecture that is already the same, essentially have a good architecture and good framework on top of which to build your features that have minimal differences between Android and iOS. If you want to check out the RIPS architecture, we've open sourced it probably half a year ago, and it's up on our GitHub as well. To close things off, a few takeaways that you should get from this talk is, the most important point, to me at least, is measuring the business cost of performance. Because it's not an obvious thing to know how much a bad performing application costs. So you should put in monitoring, you should put in things to make sure that what the baseline for you guys is, and build on top of that and do that negative A/B test to find out what your actually cost is. Investigate and commit to reliability SLOs, like service level objective is an SLO. You need to know how reliable your application needs to be. And again, it's harder to test. There's not really much A/B testing that you could do unless you want to crash the clients in a B test. So you have to at least talk with your product owners to figure out what the eventual cost of a big outage would be, and try to put in a monetary value for that as well. And ultimately, based on those decisions, make the right technology decision. Whether you want to build everything natively, or whether you want to do cross-platform technologies, or whether you want to have a hybrid app. It should be based on business principles, not sort of the need or the want to just remove half of or 1/3 of your mobile team and be able to develop your application with less people. And that's really it. I put some links up on the slides. We've got the GitHub, the RIPS GitHub repo up there. We did a few talks on RIPS. If you want to sort of get a more condensed and narrated version of what RIPS is, we've got 4 different videos on how we did the architecture rewrite and why we did it. We've got a blog post on Uber Eats and React Native up there, and we've got a link to Nanoscope, or the blog post about Nanoscope that links them to the GitHub repo if you want to check out Nanoscope. That's pretty much what I wanted to say. Thanks so much.